Hello, 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 everybody. Good afternoon, good morning, good evening, wherever you are. Welcome to the live stream today. My name is Ryan Sigler. I'm your host, a data scientist at KX. Really happy to be here. I'm joined by Michael Ryboy, developer advocate. Michael, want to say hi?
Hello, happy to be here.
Awesome. And we're really excited about the session today, which is choosing the right embedding model. You know, there's so many different embedding models out there. It takes a lot of thought and a lot of considerations to decide on the right one for your large language model application and your retrieval application. So we wanted to put this together to help people find the right embedding model for them. So with that, I'm just going to go ahead and get started here. And while people are joining, I'm going to talk a little bit about KDB AI and KX and who we are. So KDB AI, it's a vector database, and it has a couple of really cool differentiators about it. So obviously you can do your typical dense vector search, but we also have a really effective hybrid search where you can bring dense and sparse vectors together. We have really effective metadata filtering, some of the fastest metadata filtering in industry. And we also pair really well with time series data. So we have a special type of similarity search where you can actually bring in your time series data into the vector database to complete pattern matching and anomaly detection and all sorts of cool stuff. But we offer a really good free starting point for you to go ahead and try this out. And if you were interested in trying it out, all you have to do is come to kdb.ai. You go ahead in the upper right corner, you click sign up, you put in your email, and it'll go ahead and send you an email just to authenticate your account. And then once you have that, go ahead and authenticate your account. You get to set your password and then just complete your profile. So you can go ahead and put your name and your company in, and we're really interested to see, what type of use cases and projects are you looking to focus on? Are you interested in? Because these are the things then that we can tailor your experience to really be a good fit for you, and it helps us to do product planning as well. But once you do that, and that just takes a couple of minutes, you go ahead and get started with this. And this is your UX when you log in, and you get an overview of everything that's offered in KDB AI. And you can sort of see how much memory you're using. You can go and explore the tables that you have. And what's really awesome about this is once you get started, you come here and you get your API key and your endpoint. You can come over here to the sample applications tab. And we have several sample applications right here. And there's many more too if you wanted to check out all the sample applications on our GitHub. But you can open these right up in GitHub or directly in Colab if you're interested in trying these out. So if, say you wanted to get started and learn about RAG with LangChain, we have a notebook ready for you, and you can try it out yourself. And then once you have a good idea of how to use it, all you have to do is then adjust it to your use case, bring in your own data and try it. So really easy to get started. It's a really competitive offering. It's free, and it offers plenty of memory and storage and unlimited read and writes as well. Where we rank at DB Engines has us ranked #1 in the ranking of vector DB. So just to show a little bit of comparison between all of the competitors out there. And with that, just a couple things. So this session will be recorded. It's going to be available on LinkedIn and on YouTube after the session. And then also, if you're interested in learning more about KDB AI, I encourage you to join our Slack channel. So myself and Michael and Neil as well are all active on that Slack channel, answering questions that you have about vector databases, specific questions about KDB AI, or even just large language models and generative AI in general. So please go ahead and join, and we're happy to chat on there. All right, so with that, let's go ahead, and I'm going to pull up the feature session, and we're going to learn about how to choose the right embedding model. One thing as well I want to mention really quick is that there is a chat here, and we highly encourage you to join the chat and add any comments. If you have questions, comments, whatever, put them in there. We will do our best to answer those for you. And if we can answer them, we will get back to you in the comment section afterwards. So please start the discussion, ask your questions. All right, so let's get started with the feature session. How do you choose the right embedding model? All right, so the agenda for the day, first off, we're going to do a quick overview of vector databases, and then it's going to fit right into how the embedding model sort of plays in the vector database space. What is an embedding model? Where do these embedding models fit within vector databases and within the entire retrieval augmented generation pipeline? And then we'll talk about what types of embedding models are there, what are the considerations you need to have when you're deciding which embedding model to use. And then finally, we'll actually go through some of the popular embedding models out there that you could choose to use and go through some of the use cases that you might want to target them for. Okay, so again, if you want to start with KDB AI, head over to kdb.ai. Cloud version's a great option to get started. 4 gigabytes memory, 30 gigabytes storage, unlimited read and writes, and we're not going to take your tables down as long as you're still active with them. You want to build a RAG pipeline and from scratch, you can do this in like 10 minutes or less without even having an account. Once you get signed up and get that sample application running, it's just a matter of minutes. So really easy to get started. If you're interested in hosting this yourself, you have data locally, we have a server version. You can get started with that for free as well. And then we also have some offering on Azure. So plenty of options to get started. I recommend trying out cloud first. So yeah. Okay, so understanding the vector database and sort of where does this fit in with generative AI and embedding models, and there's all sorts of stuff going on here, but really at the core, a vector database is a database that you use for similarity search. So what that means is that you take your data, whatever it might be, it could be images, text, videos, audio, you send that data through an embedding model. And we're going to be talking all about these models today. But once you send it through the embedding model creates a vector representation of the original source data. This is a powerful representation because it's a numerical representation that represents the underlying semantic meaning of the original data. So it has the semantic meaning, it stores the features and the relationships of this original source data. And this is really powerful because it's not just looking at like the keywords, it's actually telling you what is being said and meant by the original data. And we're storing that in a numerical array. Other words, a vector embedding. This vector embedding is then stored in our vector database. Once we have all of these pieces of data that we're interested in embedded and stored in our vector database, a user can come and ask a question to our vector database. And then the vector database will do a similarity search to find what is the most semantically relevant data to that user's question. Then it will retrieve or it will return the most relevant pieces of data, or the most relevant vectors, if you will, and that will give you the most semantically relevant vectors that you can then pass on either to your LLM to complete a RAG pipeline or to a recommendation system or to a document search system, anything like that. So that's really the core of it. It's just a really effective and fast way to do similarity searches while keeping into account the semantic meaning of the original data. So a big part of that process is the embedding model part. So that's when you're taking your data, you're running it through this model, and then you output your vector embeddings. So what is it? It's a machine learning model, and it's trained to take in your data and convert it into this high dimensional numerical vector space. And once you do that, you're, like I just mentioned, you're capturing the features, the attribution, the semantic meaning of the original source data. And because you're taking all of your data and running it through the same embedding model, that means you can store all of these vectors that represent all of your data within the same vector space. So you can imagine all of these vectors are in the same vector space. That means we can do comparisons against them. So we can understand what are the most relevant to a user's query. can we find some way to cluster these? Can we find some ways to classify these? Because they're all held in the same vector space and created by the same embedding model, we could do all sorts of awesome applications and use cases with these vectors when they're stored in the same vector space in our vector database. One other thing that embedding models do really well is that they take your data and they're actually compressing it. So they're taking your original raw data and then compressing it into this numerical format. So it's really dimensionality reduction in a sense, and you're saving memory and increasing your search speed by doing this. But just keep in mind, obviously, anytime you're doing compression, it's going to be slightly lossy. So the more you compress, you're going to lose some information as well. So that's just something to keep in mind. And we'll talk a little bit more about the different dimensionalities available and the pros and cons of high and low dimensionalities later on in the presentation. Okay, so just a quick slide on the actual similarity search part of this. So once your vectors are created with your embedding model, you store them in your vector database, and you can sort of think about this just as a simple representation in a 2D plane. In reality, these vectors are thousands of dimensions, which is, it's hard to sort of picture that with our human minds. But this is a good representation because all of these yellow dots just represent the vectors that are within a vector space. The user can send in a query vector, and then that's stored in the vector, or that's used within the vector space to run these similarity search methods. So we can do Euclidean distance, cosine similarity, or dot product. These are three search methods that are offered in KDB AI that will find what are the most semantically relevant vectors to that query vector. And then this is really powerful because we can take these semantically relevant vectors and then pass them downstream to our large language model or other applications. Okay, one of the big and popular topics of the day is retrieval augmented generation. I'm sure you've probably heard a lot about it. But really, the core purpose of RAG is to take your data and present it to a large language model so the large language model can answer the user's questions about that data. Now, the large language model hasn't been trained on the original data, so without this process, it's not going to be able to answer questions about it, about that original data. So this general process is there's two steps. There's number one, retrieval. And to set up your retrieval step, you take your data, you chunk it up into smaller pieces. And if you're interested in chunking, we have a couple different live streams of chunking that we've done already. Look at our YouTube channel, KX Systems, to find those. But you just take your data, you chunk it into smaller pieces. You then run it through that embedding model, which we're going to be talking about today, and storing that in your vector store. Once a user sends a prompt, that prompt is actually embedded the same way that our data was embedded. So it's embedded with the same model. And that allows us to do that similarity search or semantic search between the user prompt and the vector store. We will then return or retrieve, step one, all of the most relevant pieces of data based on the user's prompt. So this is the first step of RAG. Then the second step is then augmenting, retrieval augmenting the large language model with these retrieved pieces of data and the user prompt to allow our large language model to then generate a response for the user based on this relevant and contextual data. So the embedding model is important in two steps here. Number one step is the embedding of the data that you're ingesting into your vector store. So this step right here. And then number two, when you're embedding your original user prompt. So this is very important as well. And it's important that they're the same embedding model, because then they can be stored in the same vector space. So we'll talk a little bit more about this, because in many cases, like the embeddings here would be done in batch. And then when you're just sending one through the embedding model, it's just inference. So there's some things we need to consider there. But this is where embeddings fit into the retrieval augmented generation pipeline. All right, so there's a ton of embedding models out there, especially when you're looking at text embedding models. There's like so many, and it's sort of hard to decide what would be the best one for my use case. And just a little sneak preview here, there is a benchmarking and ranking system on Hugging Face called the MTEB benchmarks. And they actually have several benchmarks that rank over 2,000 embedding models. So you can come here, and this is for text embedding models, and we'll talk a little bit more about this ranking here, but this goes into depth about all the available text embedding models and what ones rank best for different tasks, and what is their accuracy for different tasks and things like that. So there's text embedding models, and there's plenty of them, but there's also other types of embedding models. There's image embedding models. You could use something like Clip from OpenAI or ImageBind as your image embedding models. There's audio embedding models. And then, of course, there's also multimodal embedding models. So Clip and ImageBind are also multimodal. That means they can embed multiple types of data with the same embedding model. And so it just depends on your use case. If you're using text, then text is probably the one you want to use, obviously. But if you were using had data that had maybe images and text in it, then you might want to consider a multimodal embedding model. And when we think about multimodal embedding models, there's a couple different ways we could really architect this. And one of the reasons we might do this is because there's plenty of text embedding models, but there's not a ton of multimodal embedding models available out there right now. So in some cases, we may get better performance by taking all of our original data, regardless of the data type that it is, transitioning it and transforming it into the text modality first. So you can take your audio and transcribe it into text. You take your image and video, you summarize it into text. You take your text, it's already text, so you don't have to do anything. And then you pass that on to your text embedding model to get vector embeddings that are in a shared space and are technically multimodal. Even though they're created with a text embedding model, you're using transcriptions and summaries to represent your original data. So that's one way to do it. But you can also obviously do it with a multimodal embedding model where you pass everything just directly in. You don't have to do any transformations, and then you still get the created vector embeddings for all of your data, and it's all in the same vector space, meaning you can do vector search and retrieve relevant data, regardless whether it's audio, text, or video. So just a couple ways to approach multimodal embeddings. Okay, so that's a bit of background on embedding models. Now we're going to look at what are the characteristics that we need to think about when we are going to head it and choose an embedding model for our use case. And because there's so many out there, especially in the text embeddings domain, there's many different characteristics that we can take into account. So there's really two key types of embedding models, open source and closed source. So we're going to talk about each of those. Open source embedding models, you download them and you can work with them locally. They're relatively easy to work with locally. Of course, you might have to do a little setup, and you might have to host on your own infrastructure potentially, but they're free if you're processing locally, and that means it could be cheaper than paying for a closed source model. But of course, they're not going to be likely supported for cloud inference by any of the embedding model providers because they're open source. But they're really useful when you have a lot of local data that you want to process, and you don't want to send that data to a closed source provider. You don't want to send that to OpenAI or any of the other source providers. You don't want to send that over the internet. You just want to do the embedding locally. This is a perfect method to keep your data private. So this is giving you ultimate control over your search pipeline. And there's plenty of open source embedding models available as well. So there's no shortage of them out there. Now, the other type of embedding model is closed source, of course. And closed source embedding models, they often are used with API inferencing, and they're paid. The beauty of these, though, is that they're very little setup, and they have additional benefits built in. So you can just set up your pipeline, like with something like OpenAI. It's very simple to use. There's lots of good documentation, and they have some additional benefits oftentimes. Like, for example, OpenAI has the ability to take your embeddings and shorten them. So you're going to trade off accuracy for memory in that case, but some of the closed source ones have that additional capability. And oftentimes the closed source models are going to have better out of the box performance, especially for certain use cases like multilingual, where you can have certain embedding models that can understand like 100+ languages. You also have some embedding models that have an additional benefit of having instruction embedding. So you could almost think about that like doing prompt engineering for your embedding model, which is a pretty interesting thought. And even though there's closed source and oftentimes they do cost money, sometimes you can get a free trial. So Voyage AI, for example, has a free trial. I believe they have like 50 million, a 50 million token free trial if you put your credit card in. So when is this useful? When might you want to use closed source? If you don't have a ton of data and will be able to come in below that free trial mark, or are willing just to pay to embed your data, this is a good option. If you don't want to mess around with hosting your own infrastructure, hosting your own embedded model, this is a good option. A lot of times they just have better performance out of the box. So if you're looking for the best possible performance, closed source might be a good place to start. If you're iterating quickly, you just want to try this out as quickly as possible, not having to host your own infrastructure and set up your embedding model locally is, that just takes time. So if you can just call out to your API and get your embedding back in a matter of milliseconds, then this is a great way to work and work iteratively and quickly. Okay, so those were the types of embedding models. And now let's talk about how we can sort of get started with actually going out and finding the right one for us. And a great place to get started with these is with these MTEB rankings, massive text embedding benchmark. It's from Hugging Face. You can go out and Google it and find it. Basically, it's a leaderboard of embedding models, and they have over 2,000 embedding models on this leaderboard. And all these embedding models were tested on the same benchmarks, 56 data sets across 8 key tasks. So you can see the tasks here. You got clustering, classification, you got retrieval, summarization, things like re-ranking as well. So they're all benchmarked on a variety of tasks. It contains both closed source and open source models. But what you can do is you can come here, you can find what are the most performant embedding models currently in general. And then you could say, okay, I know I'm building a RAG pipeline and I need very effective retrieval. That's sort of the task that I'm interested in. Then I can come and I can sort all these embedding models by retrieval score and get the best embedding models available currently that score the highest on the retrieval task. So this is a great place just to get your mind wrapped around, like, what are the best embedding models that are available right now, even for my specific task that I'm interested in. A great place to get started. Highly recommend you check it out. And when we are looking at that leaderboard, there's some interesting columns that we can pay attention to that will tell us more about what might be the best embedding model for our use case. And the first thing, of course, you need to do is understand your use case. Like I said, if you're interested in retrieval, you could go ahead to that leaderboard and just sort by retrieval and find the best embedding model for retrieval. So does your embedding model need to have a specialization for your use case? That's the question you need to ask kind of upfront. But then there's something that I feel is sort of overlooked in a sense in embedding models is what is the maximum input tokens? So an embedding model, similar to an LLM, sort of has a context window. And you hear about LLM context windows often, but you don't hear about them quite as often with embedding models, but they have them. You can only pass a limited number of tokens into these embedding models at once. So if you're working with really large documentation, it's unlikely that all of that's going to fit into the context window of an embedding model. So we just need to make sure the embedding model that we choose actually can take the number of tokens that we're going to be passing into it. The other thing to consider is the embedding dimensionality. So when you take your data, you pass it through that embedding model, and it generates your vector embeddings. It's going to generate a fixed number, a fixed size vector for each embedding that it creates. And these vectors will be a fixed size of number of dimensions. And different embedding models output different dimensions. So if you want if you're using an embedding model that outputs smaller dimensions, say something like around 300, 384, something like that. With that, there's smaller dimensions. That means you're going to get faster computation. Your similarity searches, once loaded into the vector databases, are going to run faster because they're the vectors are less dimensions, they're less complex. You're going to have a significantly reduced memory footprint because the vectors are just significantly smaller than a vector that's like thousands of dimensions long. But of course, the downside is you're compressing your original data into 300 something dimensions rather than several thousand dimensions. So you're compressing it more. It could mean you're getting a less accurate semantic representation. Now, on the other side of the coin, if you have larger dimensions, say you're using like one of OpenAI's new embedding models, text embedding 3 large, in that case, you have like 3072 dimensions. So you're going to get extremely high expressiveness in those vector embeddings. You're going to be capturing the most possible semantic meaning within those vector embeddings. However, because they're larger, they're going to have a larger memory footprint and they're going to have slower searches. So it's just a trade-off. What is important for you in your application? Do you have a memory constraint where smaller dimensions are going to be more important, like if you're running something on an edge device? Or if you want to get the best possible representation of your original data, then larger dimensions probably are the way to go. And from here, I'm going to actually go ahead and pass it off to Michael, who's going to take you through the rest of the model considerations and talk you through some of the really popular and well-performant embedding models out there today.
Thanks a lot, Ryan. That was really great. Yeah, there are a few more considerations that I think are important for an embedding model. Just to go back to the dimensionality thing really quick. Dimensions are extremely important when you're choosing an embedding model. Generally, low dimensional models are much faster, but perform a little worse than higher dimensional embedding models. But there's actually a little advantage to higher dimensional models in that if you take a higher dimensional model, you get a vector that when quantized still performs better than a lower dimensional model. And this allows you to do very interesting things. Let's say you have an OpenAI large embedding. Well, this is going to be slow to compute, but if you quantize it, you could actually get better results than something like a really small OpenAI model. So that's just something to consider. Like this computation time isn't really something you can get around, but when you're thinking about memory, the memory you actually need to store the embeddings in your vector database, for example, well, if you have like hundreds of millions of embeddings, that really adds up, right? And you have to think about search speeds for your vector database. And at that point, quantizing your embeddings might be your only choice because you don't have like a bulky, 4 terabyte, machine. Another thing to consider is how much memory is actually needed to run the embedding model. So this isn't too important in practice, but depending on your local hardware, you might want a lighter or heavier embedding model. Sometimes you just want a really simple, very light embedding model that does the job, because for vector search, often the quality of your embeddings might not matter that much. In that case, it makes sense to just use a very light embedding model that's extremely quick, runs on any machine, could be an edge device or anything else that you have. And in that case, you won't need that much memory. Another important factor is how does the embedding model perform? What is the overall performance score? Is it accurate in the task? Does it do well in the tasks that you need it to do? The most common task is retrieval, which means, okay, like what is its accuracy? And you can define accuracy in different ways. You could see how many of the first few results are correct, how many of the first 100 results are correct. Usually what's most important is that the first few results you're passing into a large language model or showing to the user are relevant. And then you could decide, well, is the specific ordering of those few results relevant or not? For RAG, for example, it doesn't really matter that much. But there are other tasks that you could use an embedding model for. You could use them for classification and re-ranking. And for those tasks, there are other embedding models that you could rank on the MTV leaderboard that are specialized for that task or perform better for that task or perform better on your specific data. And another consideration is speed and latency. How long does it take for the model to actually create a batch of embeddings or a single embedding? So This can be split into two different types of latencies that are both important but are kind of different. So one is how long does it take for the model to create a batch of embeddings? And the because when we're actually processing and embedding our data set, well, we don't want to be waiting for many, many hours just to embed our data set, right? So we want it to be efficient in batches and embed batches of embeddings quickly. But likely more important is the latency at inference time, or we could think of it as latency with a batch of one. This is the time the user is actually waiting. So if we think of a RAG pipeline has three steps, right? We embed our query vector, we fetch from a vector database, and then we get a response from a large language model, right? We don't want this latency to actually create the embedding to be too long because that's just time the user is waiting, right? Sure, that RAG step is going to be our longest step, but if we're actually just displaying stuff to users, that vector database step could be extremely quick. It could be less than 5 milliseconds, depending on our data and our specific database configurations. We don't want this embedding step for our query vector to be too slow. So those are just some considerations that are helpful when you're choosing your embedding model. Some other considerations are whether your embedding model is general versus domain specific. So the vast majority of embedding models are general. They work for any kind of data. They basically take some data from the internet, they train these embedding models, and they work well for pretty much everything you throw at them. They might work poorly for non-English data because they're trained mostly on English data in most cases. And generally, benchmarks that test embedding models cover a wide variety of data. So in practice, when you're using an embedding model, you're likely searching over your own data. And even though these embedding models are like okay for everything, they're not necessarily going to perform well for your specific data. For example, if your specific data is in another language or is domain specific, these embedding models are just going to perform okay. They're not going to really excel at your specific data unless it's something like an English book, right? It's probably going to be more than okay for your specific book, but like if it's legal documents or scientific documents or any kind of data that's outside the norm of what these embedding models were likely trained on, it's going to perform worse. And one consideration is that there's actually general specific models, which means these are embedding models fine-tuned specifically on a domain or with a particular use case, but at a massive scale by companies like Cohere, right? Cohere has a multilingual model that performs well for a lot of languages. And if you wanted to fine tune a model like that for yourself, that would be very challenging. Voyage AI also has their legal model. I think they have a finance model. I'm not really sure off the top of my head, but they do have a lot of domain specific models. But if you're trying to use a model on your specific data, what you could do is you could fine tune a general model on your specific data. So let's say you have a lot of medical, scientific, or legal data. Well, your general embedding model can have some understanding of these topics, but it's not going to really be able to understand them at a level to search them very accurately. And there's a way to get around that without fine tuning your embedding model. And that's just to use hybrid search to mix with something like BM25 and mix keyword and embedding search. And you'll get a little bit better performance because when you have these specific domains, sometimes keyword search performs a little better. But another thing you could do is actually fine tune your embedding model on those specific domains. So a fine-tuned model can have a PhD level of understanding on a given topic. You will need a corpus of training data, and if your data is changing a lot over time, then this might not be the ideal solution. But as long as the distribution is pretty much the same, what you can do is you can fine-tune an embedding model, get 20 to 30% performance gains, and then you can add a hybrid search on top of that if you'd really like. And another thing you could do is you could shorten your embeddings. So OpenAI lets you shorten your generated embeddings. You could quantize your embeddings. So even though an embedding model is large, you could still theoretically use it, because if you are thinking about memory in your vector database, that's still something you could optimize for, even for a large model. All right, so let's go over some common embedding models. So these are just embedding models that I see a lot used in practice. Uh, and the first is the Cohere multilingual embedding model. It's really good at just multiple languages. It supports 100 languages. It is best in class for multilingual search. It is closed source, which is something to consider, but it has a bunch of different use cases. The first is multilingual semantic search, right? If you're searching across different languages, let's say your data is in Spanish, English, French, well, a person can query in English and get relevant results in French, right? This isn't necessarily what you want, but if that is what you want, this would be very useful. Another thing is for something like clustering or aggregating customer feedback. This is really useful because you can organize feedback without regard for languages, right? If you have specific feedback in English, you can find similar feedback in French, right? And this allows you to do all kinds of things that are challenging if your embedding model doesn't really understand multiple languages. So great for clustering. And there's a lot of different use cases. And training this kind of model from scratch would just be really challenging, because it's hard to teach an embedding model lots of languages without some, real machine learning experience. And it could also do something, for example, like cross-lingual zero-shot content moderation, right? So if you have, let's say you have a Discord server, for example, and you want to make a content moderation bot, right? You can just use this multilingual model to basically cluster and categorize into harmful or non-harmful in 100 languages, right? And this is really useful in practice because it really understands a lot of languages, and this is really challenging to teach an embedding model. You really have to have a very diverse data set with lots of languages, and you have to balance that data. And it's just a great job by the Cohere team, really excelling in this field. Another is OpenAI embeddings. OpenAI embeddings are very commonly used just because the documentation is great, right? They're very easy to use, excellent performance. They're not necessarily top of the line, but they're up there. They're pretty cheap. So if you have a small application or a medium-sized application or even a large application, you're probably not going to be spending too much money on OpenAI embeddings. And this is the case for closed source uh, embedding models as well. In fact, if you use these models, sometimes you're thinking, whoa, how are they making any money? Well, they're not on most people, because for most applications, they're not making money. But if someone's embedding billions or tens of billions of documents, that's when the pricing starts to get to a very high level. They're closed source, and OpenAI actually can help you reduce your dimensions pretty easily, and they'll tell you that the performance doesn't degrade too much, and they've tested this. So a lot of the times when you're quantizing vectors, it's difficult to tell how much that performance degrades. But with OpenAI, it's extremely clear. Okay, like you could quantize it in this way that they recommend, and the performance doesn't degrade. And they tested this, which is a major advantage, because you don't really want to be researching quantized vectors in many cases. And one thing is that OpenAI docs just recommend using dot product. Actually, this slide might not be correct. So basically, the OpenAI embeddings are normalized to length 1, which means that cosine similarity is pretty much the same as dot product. And cosine similarity and Euclidean distance result in the same ranking. Basically, you could use anything to calculate your cosine similarity. So what you could just do is you could speed it up a bit with dot product. So cosine similarity gets the best results, but you could calculate it with dot product or slightly faster calculations. So that's just something to consider with OpenAI embeddings. And yeah, it's pretty cheap. It performs well on MTV. The context length is actually pretty long, which is something to consider. Over 8,000 tokens, and there's a lot of options to choose from. And they're constantly updating them, and the performance is changing. But if you look at the pages per dollar, it's like 62,000 pages per dollar for a small embedding model, which is pretty cheap. But if you're embedding hundreds or of thousands or millions of pages, suddenly you might have to start thinking about costs and thinking about whether OpenAI is the best choice for you. Another option is Voyage AI. So Voyage AI recently came onto the mix, and their model started leading the MTB leaderboards around May 2024. And they're not at the very top now, but what they came out with is instruction chain embeddings that can get better performance for certain tasks. Instruction chain embeddings are interesting because basically you could prompt them kind of like a large language model. And what you do is you define the data set data, and you query and you add specific uh, information to it. You could say, this is a query vector for searching people. This is a person to be represented, right? For your dataset data. And this can improve performance. It works well out of the box. They kind of abstract this way for you. So they have this Voyage Large 2 instruct model, which has 1,024 dimensions, which for very well performing models is actually pretty low. And what this means is you could get really good performance with not a lot of dimensions, which is basically incredible, right? So they were better than all these models with 5,000 dimensions plus at the time, and they don't have a lot of dimensions. And this model is still up there. It's still performing well at the time of this video, and it has 16,000 context select tokens. So that's great. Like for a lot of use cases, you want to embed more tokens, and that's something you could use Voyage AI for. Really generous free plan, 50 million tokens embedded with free with a credit card. I think you could start without using a credit card at all. The rate limits are terrible, but it's absolutely a great experience. They're up there in terms of the best providers, and they have pretty fast inference as well, because that's their job, to provide fast inference. All right, so we talked about the closed source models, but in practice, often we want to use open source models. And the reason is they're a bit more flexible, right? Let's say we have, instead of 60,000 pages where we're paying $1 to OpenAI, we have 60 million pages, right? At this point, we don't want to be like, oh, we're going to constantly pay OpenAI every time we embed, test, work with these embeddings. No, we want a way to work and not worry about costs on our own machines, not send any data to OpenAI, not use an API platform to generate our embeddings. We want to work with it locally. And there's lots of advantages to this. And a big one is cost. So for this, we could use something like sentence transformers. So this is a Python framework for sentence, text, and image embeddings. And it works with pretty much any embedding model on Hugging Face, right? You upload an embedding model to Hugging Face, and then instantly you could use it with sentence transformers. You could load it. One problem is that it's very robust. It works for a large variety of models, but it's very slow. So in practice, if you can avoid using this library for inference, I would avoid it. Sometimes you can't, just because your embedding model only works with this library, which is fine. But there are faster alternatives out there. And one fast alternative is Fast Embed. Fast embed is a Python library for very fast embedding generation, and it's very lightweight. So it basically has only the components of sentence transformers necessary to actually generate these embeddings quickly. That's its whole purpose. And it's limited in the number of models it supports, but the advantage is that the embeddings generated are extremely fast. Sorry, the latency to generate these embeddings is extremely low. And it now supports GPU acceleration. So if you have a GPU, it's going to be even faster. So for most use cases I work with, this library is fast enough on CPU. But if you're actually like trying to embed 100 million documents, for example, and you don't have all day, then what you could do is you could use a bunch of GPUs and just get it done more quickly. And there are other libraries that do the same thing, which is fast embedding generation. But I just found that personally, this one is really easy to work with. So that's the one I'm going to recommend today. Another option is text embedding inference, which is actually written in Rust and is extremely optimized. And I don't think I have a slide for that today, but text embedding inference has a lot of advantages in that it's so fast. It's incredibly fast. And if you're actually doing inference on a single vector, right, at query time, it's basically free for most models. So it's like a millisecond on a GPU or less than 5 milliseconds on a CPU. So we'll get to that in a minute, talking more about latencies, but just it depends. Fast embed, it's great for actually processing your data set, but if you're processing your query, there are other options that are even faster. So let's talk about embedding time for 5,000 texts. We could think of these as chunks. These are just sentences that I embedded. And this is a really rough benchmark that I just created, and it's not extremely accurate. And there's a lot of stuff here that might be different from you because here there's like over the wire time, all these different things to consider. But in general, you could see that the time to generate 5,000 texts is variable, right? We have OpenAI, Voyage, Cohere being pretty much the same. Cohere is a little slower, but it does take relatively the same amount of time as fast embed on a CPU. Fast embed on a GPU is much faster. So there's not really a major latency advantage to embedding using a provider compared to locally, at least for your data set. So if you're using these closed source embedding models, it's probably going to be because they perform better on your specific data. That's the time that I recommend using these. Or another time is when you don't want to worry about embedding inference. So they handle embedding inference for you at query time. And if you don't really care about query time inference latency, then just use any of these and use the one that performs best on your data. Now, let's talk about embedding latency at inference time. So at inference time, we have a single query that we're embedding, which means our batch size is pretty much one, right? So because these closed source embedding providers, they embed in batches, right? They take a lot of requests, they batch them, and to save costs, they basically process them and embed them in batches, which means you get slower results, right? So for OpenAI, you see that you get a P95, which means at the 95th percentile, the 95th slowest percentile, you get 50 millisecond or around 47 millisecond response times. On average, 25 milliseconds. And what this means, sorry, I misspoke, 250 milliseconds and 470 milliseconds. So 250 milliseconds, that's really slow in practice. Like it's you shouldn't be waiting this long to get a response from at inference time, because if you have some kind of search engine, 250 milliseconds just for this part of your search is just too slow. And Cohere does a lot better than OpenAI and Voyage. So if you really care about query latency, then Cohere seems to perform better. Again, these benchmarks aren't ideal. You should do your own benchmarks, because there's a lot of things that goes into embedding latency, and probably the most important thing is the length of your data, right? I did this on very short sentences. If you have really long chunks, then your embedding latency is going to be much longer. So experiment on your own data and figure out, when you're choosing an embedding model, hey, does this provider embed quickly enough for me? And if it doesn't, then it kind of eliminates it from your options. We see that fast embed on a CPU performs better than OpenAI and Voyage for a single vector. Now, how will this handle lots of throughput? Maybe not well, right? If you have a lot of queries coming in, but there are faster options like text embedding inference. They're much faster than fast embed. So that's just something to consider, because often you don't want 250 millisecond wait times for your embedding inference. Another thing to consider is re-ranking models. So we could think of vector search with embeddings as casting a very wide net. You're just hoping that something sticks, right? And in practice, this gives us decent search results, but the understanding of embedding models of your data is only so robust, because these embedding models are fast, and there's something called buy-in cutters. So you embed your query and you embed your document separately, and then you do a mathematical operation using a vector database usually, and then you find their similarity. So what you could do is use a re-ranker to actually improve this. So you have your data, you chunk it, you embed it, you insert it into your vector database. And then at query time, you have a user prompt. You embed that user prompt. You run a semantic search. You get some chunks from your vector database. Here I have top 25 relevant chunks, but in reality, you might want to use more. And then you could use a re-ranker to get the top 3 most relevant chunks, or to get a better ordering on these top 25. So because embedding models cast a very wide net, re-ranker models actually have a better understanding of the relationships between query and documents, so they could get a much better ranking. So what it might make sense to do is take up to 1,000 results, pull that from your vector database, and then re-rank those. That's the way to get truly the best results, but you have to think about stuff like latency, because re-rankers are pretty slow in practice. So do you really want to add another 100 millisecond step to your pipeline? That's just something to consider.
And actually, there was a question about re-rankers to consider. So can you see that question, Michael?
Yeah, I know that MTB does have a re-ranking tab. So if you go to MTB, there is a section for re-rankers. I haven't explored it too much, but I know Gina has a popular re-ranker that's open source. BG Reranker Large, I think I've heard of. I recommend the re-rankers that come with text embedding inference, because if you're actually implementing a re-ranker, and it seems like you're interested in open source re-rankers, you want to be able to actually run it extremely quickly. So text embedding inference is probably the best way to actually run a re-ranker in practice. And it's crazy the difference in latency you get running a re-ranker yourself versus a closed source re-ranker. The advantage of closed source re-rankers is that it feels magical as a developer. You add one line of code, you pass your data to your API from your vector database. Vector database returns some results that are kind of relevant, and then suddenly you have really relevant results. And this feels great as a developer. It really does. But if you start implementing your own re-rankers, suddenly it's even more magical, because you get the same thing. Maybe your results are a little worse because these closed source re-rankers tend to perform a little better, but you get it in a few milliseconds. And it's a really cheap way in terms of inference time to get much better results. So I hope this answered your question. I'm still playing around with actually, playing around and implementing pipelines with closed source re-rankers. I've mostly used, with open source re-rankers. I mostly play around the closed source re-rankers. But that's a really good question. Thanks for asking it, Anton.
Thanks, Michael. Yeah, great question. And that, I believe, is the last slide in our presentation. So if there's any other questions, put them in the chat. And I actually got one more I'm going to put up right here for us, Michael. Let's see. This goes back to the benchmarks a little bit. And if you've explored benchmarks with a relation between the size of the vector and latency.
Size of the vector and
or the input size, how many tokens we're passing into the embedding model.
Yeah. Oh man, that's actually, so a lot of benchmarks. One thing that's frustrating is that they don't really deal with latency. And the reason for this is that you could kind of know how fast they're going to be based on the embedding size, right? The number of dimensions in the vectors that are outputted. And this is like pretty consistent across embedding models. So in general, the more tokens you're embedding, the slower it is. And if your chunks are quite large, this could be a very substantial difference, right? So that's something to consider. But the good news is when you're processing with a vector database, your query is usually very short, right? Because the thing coming from your user. So this is going to be, it's not going to be a lot of tokens. So it's going to be pretty fast. What's going to be slow is going to be embedding your data set. But the thing is there that you can take your time. You can take your time and you can just, even if your embedding model is slow at embedding lots of tokens, just, spin up another machine, right? So it's not really that much of a problem in practice unless your query vector is a very large number of tokens, and then you have to worry about the latency and for the user to get a result. But the thing about vector databases is that they compare your query vector, which can be very small and computed very quickly, to your documents, which are large and computed slower, but they're computed beforehand. So that's just something to consider. And that's a really good question. But in practice, the real answer is just to test yourself.
All right. Well, thank you, Michael. And I know we're about coming up on the hour here, so I think we'll call it there. But there's some more questions, and we'll respond to those in the chat shortly after the session. This session has been recorded, and it will be available on YouTube and LinkedIn directly after the session. So I just want to say thank you, everybody, for joining and taking the time to come learn with us. We really appreciate it. And thank you, Michael, for your piece of the presentation. Really insightful.
Thanks, Ryan. Thanks for so many questions, guys. Like this was really good. Yeah, I'm excited to answer these later.
Yep, we'll definitely be getting to these questions later. And again, if you're interested in trying out KDB AI, go to kdb.ai and sign up for an account. You get started doing all sorts of cool applications and samples in a matter of minutes. So check that out. And we will be doing more sessions very soon. So keep posted, and we'll see you soon. Thanks for joining. Have a good day.
Later. Thank you so much.